Welcome to the acid-base concentration calculation tutorial. Boy, that's a mouthful. In this calculation tutorial, we are going to cover four types of concentration calculations. The first type of problem is going to be simple. We're just going to calculate the concentration of hydrogen ions using the Kw expression. In the second type of problem, we're going to start with a realistic strong acid. And in this strong acid, we're going to then calculate the hydrogen ion concentration and the hydroxide ion concentration. Again, we'll have to use the Kw expression. In the third and fourth types of problems, we're going to calculate the hydrogen ion concentration in weak acids. To do that, we're going to have to use a Ka and an ice chart. Each of the problems will be introduced with some focus tips and then concluded with some thoughts and questions that you might want to consider to gauge your own understanding. Alright, in this first problem, we're going to have to calculate the hydrogen ion concentration using the Kw. It's going to be a very simple problem. The hydroxide ion concentration will be given, then you'll just have to use the expression for Kw, and you'll have to have memorized that the Kw equals 1.0 times 10 to the negative 14th. That's a number that you're going to want to remember. Another thing to focus on in this first problem is the use of units in the Kw expression.
What is the hydrogen ion concentration in a solution with a hydroxide ion concentration of 2.5 times 10 to the negative 8th molar? Is the solution acidic, basic, or neutral? The first thing we do is identify the hydroxide ion concentration and then identify the fact that the hydrogen ion concentration is absent. That's the thing we're looking for. To solve this problem, we need to use the expression for Kw. Kw equals the concentration of the hydrogen ions times the concentration of the hydroxide ions. Next, we rearrange this expression for Kw to solve for the hydrogen ion concentration. In this case, Kw will be divided by the hydroxide ion concentration. Next, we substitute the two values for the Kw, which is a known number, a constant, 1.0 times 10 to the negative 14th, divided by the hydroxide ion concentration, which we identified as being given to us in the problem, 2.5 times 10 to the negative 8th. We divide those two numbers and we get that the hydrogen ion concentration is 4.0 times 10 to the negative 7th molar. You can see that the hydrogen ion concentration is greater than 1.0 times 10 to the negative 7th molar, which means that this solution is acidic. Notice that we did not put units in with the numbers that we substituted in, and that's because the constant for Kw is a unitless number, so you should put all numbers into the expression without units.
Now that you've done the problem, I want you to think about a couple of things. What did I do to solve for the hydrogen ion concentration algebraically? In other words, what algebraic steps did I use to solve for the hydrogen ion concentration? In addition, I would like you guys to think about what you would have to do if you had to solve for the hydroxide ion concentration instead of the hydrogen ion concentration. In this second concentration calculation, you will have to use stoichiometry and a Kw expression to solve for the concentrations of hydrogen ions and hydroxide ions in a strong acid. When you're doing the stoichiometry for this problem, I want you to focus on canceling the units, as I always ask you to do for all stoichiometry type problems.
3.2 grams of nitric acid is dissolved in 250.0 milliliters. Calculate the hydrogen ion concentration. To solve this problem, we first need to identify the ionization equation for nitric acid. As you can see, it breaks down into hydrogen ions and nitrate ions in aqueous solution. The next thing we have here is the stoichiometry to solve for the number of moles of hydrogen ions. We start off with the given number of grams of nitric acid. We use the molar mass, 63.0 grams of nitric acid, to convert to moles of nitric acid. Then we use the ratio of 1 mole of nitric acid to every 1 mole of hydrogen ions to determine that the hydrogen ion mole number is 0.051 moles. To determine the hydrogen ion concentration, we take the mole amount that we just solved for using stoichiometry and divide it by 0.2500 liters, which is the number of liters for 250 milliliters. Doing this, we get 0.20 molar hydrogen ion concentration. Even though this problem is not asking for it, we could calculate the hydroxide ion concentration for this problem by using the expression for Kw. In this case, we'll have to take the expression for Kw and rearrange it algebraically to solve for the hydroxide ion concentration, which will equal the Kw divided by the hydrogen ion concentration. Next, we substitute the value for Kw, 1.0 times 10 to the negative 14th, divided by the concentration of the hydrogen ions that we just solved for, 0.20. Notice again that we did not put units into this expression. Next, we divide those two numbers and solve for the hydroxide ion concentration. Here we get 5.0 times 10 to the negative 14th molar.
Now that you've completed the problem, I want you to think about how I converted the 250 milliliters into 0.2500 liters. You should remember your conversions, that there are 1,000 milliliters in 1 liter. Also, I'd like you to think about how I algebraically solved for the hydroxide ion concentration. In this third concentration calculation, we're going to take a look at a weak acid. To solve for the concentration of hydrogen ions in a weak acid, we're going to need to use a Ka and an ice chart. In addition, we're going to have to use a Ka expression. I also want you to pay close attention to the fact that the concentration that is given for the HF is the initial concentration that gets plugged into the ice chart.
Calculate the Ka of hydrofluoric acid if a 1.40 molar solution of HF ionizes to form a hydrogen ion concentration of 0.031 molar. The first thing you need to do is balance the ionization equation for the weak acid hydrofluoric acid. Because it is a weak acid, we use the double-sided equilibrium arrow. Hydrofluoric acid and water are the two reactants, and hydronium ions and the conjugate base F- are the two products. The next thing we need is an expression for Ka. The expression for all Kas is the conjugate base times the hydronium ion concentration divided by the concentration of the weak acid. And in this case, we have the concentration of F- times the concentration of hydronium ions divided by the concentration of HF. The next thing we need to do is develop an ice chart. The ICE stands for Initial, Change, and Equilibrium. We must determine the values of the initial concentration for the weak acid, for the hydronium ions, and for the conjugate base. Notice that we do not need the concentration of the water, and that's because it is a liquid and does not appear in the Ka expression. We figure out the initial concentration of HF by the 1.40 molar solution that is given to us in the problem. The reason that this is the initial concentration of HF is because this is how much of the weak acid is dissolved in total. The initial concentration of hydronium ion is 0, and the initial concentration of the conjugate base, F-, is also 0, because initially neither one of those two things is ionized into the water. Next, let's take a look at C, the change. For each of the items, we have to figure out how it's going to change by the value of x. C is negative x for HF because that's how much it's going to decrease by as it ionizes. C is plus x for both the hydronium ion and the F- ion because each one of those things will increase by x as the hydrofluoric acid ionizes. Therefore, at equilibrium, the E value, the concentration of HF will be 1.40 minus x, and the concentration of the hydronium ion and the F- ions will both be x. X equals 0.031 molar because this is how much is given to us in the problem. If we know that x equals 0.031 molar, then that is the concentration of hydronium ion and F- ion. And then we can determine the concentration of HF by the equation 1.40 minus x, which is 1.40 molar minus 0.031 molar equals 1.37 molar. So there we have it. We now know the equilibrium concentrations of HF H3O plus, and F minus. Now that we know those three concentrations, we can substitute them into the Ka expression, which just showed up. The Ka equals 0.031 times 0.031 divided by 1.37. Notice here again, just like with the Kw, it all comes out to unitless numbers because the Ka is a unitless number. Therefore, do not put in the molarities of each of those values into the Ka expression. And there we have it. We divide all those numbers and we get that the Ka equals 7.0 times 10 to the negative fourth.
Now that we've completed the problems, I'd like you to think about what would happen if there was coefficients in our equilibrium equation for the ionization of hydrofluoric acid. In other words, I'd like you to think about what the x values would be. Would they just be plus x's and minus x's? What would the coefficients do to those x values? We've talked about this before. In this fourth calculation, again for a weak acid, you're going to be given the Ka value and you're going to need to solve for x, or the hydronium ion concentration. In this problem, I'd like you to focus on the trick that we use to simplify the expression for Ka, getting rid of the x that's in the denominator of the equation. This is a very important trick that makes the algebra much easier.
A solution of acetic acid contains 12.0 grams of the acid in 500 milliliters of solution. Calculate the molar concentration of the hydrogen ions in this solution if the Ka for acetic acid is 1.8 times 10 to the negative fifth. Again, the first thing we're going to need is an equilibrium expression, or an equilibrium equation, for the ionization of the weak acid, acetic acid. Again, because it's a weak acid, we see the double-sided arrow. And again, we see as the product hydronium ions and the conjugate base, which in this case is the acetate ion, C2H3O2-. Because in this problem, concentration is not given to you right off the bat, we have to use a quick stoichiometry calculation to determine the number of moles of the acetic acid that is mixed into solution. We start off with the 12.0 grams, and then we use the molar mass of acetic acid, 60.0 grams, which was determined from the periodic table, to calculate that there is 0.200 moles of acetic acid in this solution. To figure out the concentration of acetic acid, we have to divide that 0.200 moles divided by the number of liters, which was 500 milliliters converted to 0.5000 liters, giving us a concentration of 0.400 molar for the acetic acid. Next, again, we're going to need a Ka expression for this weak acid. Of course, it's the conjugate base times the concentration of hydronium ions divided by the weak acid. In this case, we have the concentration of the acetate ion times the concentration of hydronium ions divided by the concentration of acetic acid. Again, we're going to need an ice chart for a weak acid calculation. In this case, the concentration that we calculated using stoichiometry is the initial concentration of the acetic acid, 0.400. We can see that in the I row under acetic acid. In the initial I row for the hydronium ion and the conjugate base, the acetate ion, we can see that again we have 0 and 0 because initially none of it has ionized yet. Again, because the coefficients of our equilibrium reaction are all just 1, then the acetic acid is going to decrease by a value of x, while the concentrations of hydronium ion and the acetate ion are going to both increase by positive x. Therefore, at equilibrium,
the concentration of the acetic acid will be 0.400 minus X, and the concentrations of the hydronium ion and the acetate ion will both be 0 plus X, which just comes out to X. Therefore, if we substitute those values into our Ka expression, we see that we have X times X divided by 0.400 minus X. Well, here's where we can do a little trick. 0.400 minus X is actually just about the same as 0.400. And that's because this is a weak acid, which only ionizes very, very little. So little that if you subtract it from the 0.400, you basically get 0.400. So now our Ka expression simplifies to Ka equals X squared divided by 0.400. This, of course, makes the algebra a lot easier. The next thing we're going to have to do then is substitute the value for Ka and solve for X squared. Well, let's solve for X squared first and reduce it down to just solving for X. To do that, we're going to have to multiply Ka by 0.400 and then take the square root of the whole thing. And there you have it. X equals the square root of 0.400 times the Ka. Now we'll substitute the value for the Ka into the equation. The Ka value was given to us in the problem. Ka equals 1.8 times 10 to the negative fifth. And there it is. X equals the square root of 0.400 times 1.8 times 10 to the negative fifth. And now we solve for X, which is also the hydronium ion concentration. X equals 0.0027 molar. Now that we've completed the problem, I'd like you to think about how we solved for X. Make sure you know how to algebraically solve for X squared by taking the square root of the equation for X squared. In chemistry, we're only worried about positive values for molarities. Therefore, we don't have to worry about the negative X that you would get if you were solving for X squared in a math class. It makes no sense for us to actually have a negative molarity.